For nearly 40 years, every textbook, every planetary model, every piece of mission planning built around the planet, Uranus rested on a single afternoon of data. One spacecraft, one pass, one brief window lasting a matter of hours, collected in January of 1986, that scientists have spent decades treating as the definitive, representative truth about an entire planet and everything orbiting it. Nobody ever got a second look. There was no follow-up flyby to check the numbers. No orbiter sent later to verify the readings. Nothing but that one narrow window, filed away and treated as permanent scientific fact for the rest of an entire generation of researchers' careers. In late 2024, a team at NASA's Jet Propulsion Laboratory went back and reanalyzed that data more carefully than anyone ever had. And what they found should genuinely unsettle you. Not because anything supernatural is lurking out there, but because of what it reveals about how much of what we confidently call scientific fact might be resting on exactly this kind of shaky, unrepeatable foundation. Here's what NASA actually found when it went back and looked closer, and why the implications reach far beyond a single ice giant at the edge of the solar system. To understand why this reanalysis matters so much, you first need to understand just how thin our knowledge of Uranus actually is, and has always been. Uranus sits nearly twice as far from the Sun as Saturn, a strange, sideways rotating ice giant tipped over almost completely on its axis, spinning more like a rolling ball than a standard top the way every other planet in the solar system does, likely the result of some catastrophic collision early in its history that nobody has ever fully explained. And in the entire history of space exploration, exactly one spacecraft has ever visited it up close. NASA's Voyager 2, already years into its historic grand tour. Of the outer solar system, swept past Uranus on January 24, 1986, capturing our first, and to this day, only close-up look at the planet, its rings, and its major moons. The entire encounter, from the moment Voyager 2 crossed into the planet's magnetic influence to the moment it exited on the other side, lasted only a matter of hours. A single fleeting pass through a system that had taken billions of years to reach whatever state it happened to be in that particular week. Everything humanity currently understands about Uranus in any real physical detail traces back to that single flyby, followed by nearly 4 decades of scientists working exclusively from that one data set with no second visit, no follow-up mission, and no way to double-check anything Voyager 2 recorded against a fresh set of eyes. What Voyager 2 found during that flyby was strange enough on its own to keep scientists puzzled for the following 38 years. Alongside the discovery of new moons and additional rings, the spacecraft measured Uranus's magnetic field and found something bizarre. A field tilted at a wildly oblique angle relative to the planet's own rotation axis, roughly 59 degrees off, and additionally offset from the planet's actual center, unlike the comparatively clean, well-aligned magnetic fields found at every other magnetized planet in the solar system, from Earth's own reasonably tidy field to the more powerful but still roughly axis-aligned fields surrounding Jupiter and Saturn. Even stranger, the magnetosphere itself, the protective bubble of magnetic influence surrounding the planet, appeared to be almost completely empty of plasma, the charged particle material that fills equivalent regions around planets like Jupiter and Saturn, typically supplied in enormous quantities by volcanically or geologically active moons orbiting nearby. And yet, despite that near-total absence of plasma, Voyager 2 also detected unusually intense radiation belts surrounding Uranus, among the most energetic found anywhere in the solar system, second in intensity only to Jupiter's own famously brutal radiation environment. Scientists were left holding 2 measurements that seemed to directly contradict each other. A magnetosphere, apparently drained of the very material that typically feeds intense radiation belts in the first place, sitting right alongside some of the fiercest radiation belts ever recorded, a contradiction nobody had a fully satisfying explanation for over the following decades. For decades, the leading explanation researchers settled on involved Uranus's 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. At other icy moons throughout the solar system, like Saturn's Enceladus, geological activity, cracks, geysers, and internal heat can feed material directly into a planet's surrounding magnetosphere, supplying exactly the kind of plasma Uranus's own magnetosphere appeared to be missing, essentially acting as a constant fountain replenishing the charged particle environment around the planet they orbit. Since Voyager 2 detected essentially none of that plasma around Uranus, the natural conclusion scientists drew was that its moons must simply be geologically dead, inactive worlds with nothing meaningful happening beneath their icy surfaces, unlike some of their more dynamic counterparts elsewhere in the outer solar system. That conclusion became the standard, widely accepted interpretation baked into essentially every model of the Uranian system built over the following 38 years, treated as settled scientific background, rather than an open question still worth revisiting. repeated in textbooks and review papers and mission proposals, without anyone circling back to seriously question whether the original data it was built on had actually been representative of anything typical at all. Then, in November of 2024, a team led by Jamie Jasinski, a space plasma physicist at NASA's Jet Propulsion Laboratory, published a study in the journal Nature Astronomy that pulled that entire foundation out from under decades of assumptions. Jasinski's team went back through the raw solar wind data Voyager 2 had collected in the days and weeks leading up to its actual encounter with Uranus, effectively reconstructing the space weather conditions. The spacecraft was flying through in the lead-up to the flyby itself, data that had technically always existed, sitting quietly in NASA's archives for decades, but had never been closely scrutinized in quite this way. Nobody had ever thought to go back and ask a fairly basic question. What was happening upstream in the solar wind itself in the days before Voyager 2 actually arrived? What they found was almost impossible to ignore once they saw it clearly laid out. In the days immediately before Voyager 2 reached Uranus, the density and speed of the solar wind, the constant stream of charged particles flowing outward from the sun, had been steadily climbing. And by the moment the spacecraft actually arrived, the dynamic pressure of that solar wind had spiked to roughly 20 times higher than it had been just a week earlier, an enormous, rapid escalation by the standards of typical solar wind variability at that distance from the sun. That kind of pressure spike has a direct, dramatic physical effect on a planet's magnetosphere. Under normal conditions, researchers estimate Uranus's magnetosphere extends outward to roughly 28 times the planet's own radius, a substantial protective bubble by any reasonable standard. Under the compressed conditions, Voyager 2 actually flew through. That same magnetosphere would have been squeezed down to something closer to 17 times the planet's radius, a dramatic, temporary collapse driven entirely by an unusually intense burst of solar activity that happened to be washing over Uranus at exactly the moment the spacecraft showed up, shrinking the entire protective envelope by well over a third in the span of a single week. When Jasinski's team examined roughly 8 months of solar wind data surrounding Uranus's orbital position to see just how unusual this particular spike really was, the answer was almost eerie in its specificity. The flyby had occurred during the single most intense period of solar wind pressure recorded across that entire 8-month stretch, the absolute peak of an entire season's worth of space weather data. Arriving at precisely the wrong moment out of hundreds of possible days, it could have shown up instead. As Jasinski put it afterward, they had simply caught Uranus at a freak moment in time. His own assessment of what that meant was direct and, frankly, a little unsettling for anyone who has spent a career building on Voyager 2's original data. If you had known that going in, he said, you would have questioned everything Voyager 2 measured. According to the team's calculations, a magnetospheric compression this extreme shows up in the data less than 5% of the time. In other words, humanity's entire physical understanding of Uranus, built from the only close-up visit any spacecraft has ever made, was almost certainly capturing an anomalous, unrepresentative snapshot, rather than anything resembling the planet's normal everyday state. Jasinski summed up the counterfactual bluntly. If Voyager 2 had simply arrived a few days earlier, before that solar wind event compressed the magnetosphere, it would have observed a completely different magnetic environment at Uranus entirely. And the scientific narrative that has shaped 4 decades of research, textbooks, and mission planning might never have existed in anything like its current form. Here's where the story stops being simply an interesting historical footnote and starts becoming something with real, forward-looking consequences. That severe compression offers a much more elegant explanation for both of Voyager 2's original contradictory measurements at once. A magnetosphere, violently squeezed by an intense solar wind event, would naturally have much of its resident plasma driven outward and away, which would explain the near-total absence of plasma Voyager 2 recorded, without requiring Uranus's moons to be geologically dead in the first place. At the same time, that same compression event could plausibly explain the unusually intense radiation belts Voyager 2 detected, since compressing a magnetosphere can accelerate and energize trapped electrons, potentially supercharging exactly the kind of radiation belt Voyager 2 found waiting there. 2 measurements that had contradicted each other for 38 years suddenly fit together cleanly, once you account for the fact that the entire system was caught mid-squeeze by a passing burst of solar weather. And that reopens a question that had been treated as closed for decades. Whether Uranus's major moons might actually be geologically active after all, potentially even hiding subsurface oceans beneath their icy surfaces. The same basic feature that has made moons like Europa and Enceladus such compelling targets in the search for potentially habitable environments elsewhere in the solar system. If the missing plasma Voyager 2 recorded wasn't actually evidence that the moons were quiet and inactive, but was instead simply a side effect of a temporary, unrelated compression event, squeezing the entire system at exactly the wrong moment, Then the door swings back open on a possibility researchers had mostly written off years ago, that Miranda, Ariel, Umbriel, Titania, and Oberon could be considerably more dynamic and considerably more interesting from an astrobiology standpoint than the scientific consensus built on Voyager 2's data ever gave them credit for. Miranda in particular has always stood out in Voyager 2's original images as a genuinely strange little world, covered in enormous cliffs, sharp ridges, and jumbled terrain that looks almost like it was shattered and stitched back together, exactly the kind of chaotic surface geology that researchers associate with past or ongoing internal activity elsewhere in the solar system. For nearly 40 years, that visual evidence sat somewhat awkwardly alongside the magnetospheric data, suggesting the moons were dead and quiet. This reanalysis finally offers a coherent explanation for why those two lines of evidence never quite lined up. Sit with that for a second, because this is really the unsettling core of the whole story. For 38 years, an entire body of scientific literature, an entire generation of planetary models, and a considerable amount of mission planning were all built on the assumption that Uranus's moons were geologically dead worlds, a conclusion drawn directly and confidently from a single spacecraft's single afternoon of measurements. That conclusion wasn't reckless or unscientific at the time. It was the most reasonable interpretation anyone could draw from the only data that existed, built by careful, competent researchers doing exactly what good science demands, working rigorously from the best evidence available to them. But it was also, as it turns out, very possibly wrong, not because the instruments malfunctioned or the scientists made a calculation error, but simply because the spacecraft happened to arrive during an extraordinarily rare 5% window of unusual space weather, and nobody had any way of knowing that at the time, because nobody had yet thought to go back and check the solar wind conditions leading up to the encounter itself. There was no second flyby to compare it against. No follow-up mission to check the numbers a different day. Just one data set, treated for decades as the ordinary representative truth about an entire planetary system, when it may have actually been closer to catching a rare storm and mistaking it for the planet's permanent climate. That's the genuinely uncomfortable question this reanalysis leaves hanging over the rest of planetary science. How many other conclusions about the solar system, drawn from a single flyby, a single measurement, a single unrepeatable moment in time, are quietly resting on the same kind of shaky, unverified foundation, simply because nobody has ever had the opportunity to go back and check? Space exploration, by its very nature, rarely offers second chances. A flyby happens once, a landing happens once. The spacecraft moves on, the mission ends, and researchers are left working from whatever narrow slice of data they managed to capture during that single encounter, often extrapolating an entire planet's typical behavior from a window measured in hours. Voyager 2's own earlier flyby of Neptune in 1989 offers exactly the same kind of caution, since that flyby too was a single, brief pass, never repeated, and never independently checked against a second visit. Uranus just became the clearest, most well-documented example of exactly how badly that kind of extrapolation can go wrong, and there's no particular reason to assume it's the only place in the solar system where something similar might be quietly hiding in plain sight, waiting for some future researcher to finally think to ask the same basic question Yashinsky's team finally got around to asking about Uranus. There is at least a genuine path forward here, rather than this simply remaining an open, permanently unresolved mystery. In 2022, the National Academies of Sciences, Engineering, and Medicine released its once-per-decade Planetary Science Decadal Survey, the document that effectively sets NASA's priorities for major missions over the following 10 years, and it named a dedicated Uranus orbiter and probe as the top priority flagship mission the agency should pursue in the current decade, ranking it above every other candidate destination under serious consideration at the time. If that mission ultimately moves forward, it would give scientists their first real opportunity in nearly 40 years to directly observe Uranus's actual magnetosphere over an extended period, rather than relying on a single, possibly anomalous, afternoon frozen in 1980s data, and it would carry vastly more capable instrumentation than anything Voyager 2 had access to during its brief pass, including modern plasma detectors, magnetometers, and imaging systems built with technology that didn't exist when Voyager 2 launched in 1977. An orbiter, unlike a flyby, could watch the magnetosphere respond to weeks or months of genuinely varying solar wind conditions, finally building the kind of long-term dataset needed to know what Uranus's magnetic environment actually looks like on an ordinary day, rather than relying on a single afternoon that turned out to be anything but ordinary. Jashinsky himself noted that modern instrumentation alone would likely revolutionize the kinds of discoveries a return mission could make, entirely apart from simply getting lucky enough to arrive during more typical conditions. Here's what's genuinely worth sitting with once you step back from the technical detail. This isn't a story about aliens or hidden dangers or anything conventionally frightening in the way that word usually gets used online. It's something quieter and, in its own way, considerably more unsettling. A direct demonstration of how much confidently stated scientific fact can rest on a single, unrepeatable moment of observation, treated as permanent truth simply because nobody has ever had the chance to check it twice. Uranus didn't change between 1986 and 2024. The planet's moons didn't suddenly become more interesting. What changed is that scientists finally went back and asked a question nobody had thought carefully enough to ask the first time. Was the day Voyager 2 showed up actually a normal day at all? The answer, 4 decades later, turned out to be no, and that single correction has the potential to reopen one of the most compelling astrobiology questions in the entire outer solar system. Questions that had quietly been treated as closed for almost the whole time you've been alive. If stories like this are what you come here for, hit subscribe, turn on notifications, and let me know in the comments what other single flyby facts about our solar system you think might deserve a second look. Because if this reanalysis is any indication, Uranus almost certainly isn't the only place where the truth turned out to be very different from that one brief, unrepeated glimpse we've been building our understanding on for decades.